Okay, students, we have the next lecture in line. I think it should be lecture 29, if I am not mistaken. In the last lecture, we were talking about sedimentary rocks, and we were talking about loose sediments. We were also talking about that the main idea is that we said that we will be talking about fluvial sediments because we don't have time. We just have another 2 weeks. So fluvial sediments that are driven by waters and river systems or so. And the important point here is that the sediments are brought from a great distance, and they are transported on a flatter trajectory and then finally deposited in a basin, which is a depression. It could be a lake, and it could be a sea. It could be the oceanic part of the ocean. It could be an ocean basin, it could be a lake, it could be anything. So long that there is a depression, sediments would be deposited in this. And we were also talking of settling velocities last class, and so we know in general that sediments, when they're deposited, they are graded according to the size and or the density, and we have discussed this before. It's also important to realize the length of the water column, since if you have to separate them in a perfect order, that means the largest sediment at the bottom, then you have the smaller sediments, and the smaller sediments, you need a long water column. And finally, it is also important to realize that if sediments are deposited, if the distance between the sediment source and the point where the sediment is deposited, if that is small, then most of these clasts or the detrital material that is carried by the water, they are not well rounded or not very spherical. And I asked you to read about sphericity and roundness, and that the sizes also are not very well graded. And so, but what we finally see is, we don't see the erosion, we don't see the weathering, we don't see the transportation unless you're seeing it on the river right now. But normally in older rocks, what we see is the final product, which is the sedimentation. And what happens when loose sediments are deposited, there is a pile-up of sediments, and because of this, there are pressure acting from the top downwards, and so sediments, they tend to clink each other, and there are pressure solutions. Then solutions percolate through the sediments and they are replaced, and so a sediment is lithified into a sedimentary rock. Today we will be talking of sediments. Now, when you have a sediment, you normally don't have only one size. You can have it. It's not that it's uncommon. You can have very unimodal sizes of sedimentary rocks. But generally we can see that sedimentary rocks do not have a perfect grain size. They have a range of grain sizes. Now we talk about how then we can understand about the sediments a little bit. And for that we need to know what is a little bit of statistical things, and there are certain statistical definitions. I have put in here certain statistical values, statistical equations which are very simple to follow, but very modern techniques involve very well thought of statistical equations, which is not necessary at this stage, because I think what is important is to understand the logic, and not the complexity of the equation is not important at the moment at this stage of your acquisition of knowledge. Now, what I am giving you, this is a table where and I also told you in one of these early lectures, so when you get a sediment, you put them under a sieve, and then you shake the sieve. And so if you put a known amount of the sediment on the top, and when you sieve it, the sediments grade them, and they're separated by pans of different sizes, and so the sediment collects on the sediment sieves, and we can find out what is the proportion or what is the weight of the sediments that are deposited on each sieve, indicating that sieve up and the sieve on which it is deposited, they will give you the size range of it. So this is also called the weight fraction, or it's also called frequency. So generally, as you know from the Wooden-Wentworth scale, which I gave you before, that the grain sizes are separated into millimeters, sand, conglomerate, and they are distinctive sizes, the diameters. Normally they are given on a millimeter scale. So this is a typical analysis that is found out from a sieve. So you put in a particular amount of sediments. The blue lines, the blue numbers here that I have written to you, the actual numbers will become important later. But first is, the first column gives you the size range. So that is the size range over which the sediments, or a particular sediment, was sieved, and the collected sediment was, say, according to the size range. So 16 to 8 millimeter diameter, 8 to 4 millimeter diameter, 4 to 2, 2 to 1. And this you can do it yourself. It all depends on you, how you want to do it, depending upon your work. And these values in the blue, we have three samples, 6, 10, and 3. We have 3 samples, 6, 10, and 3. So in the sample 6, for example, or each sample has two, you can see 2 columns, one in blue and one in red. So these are the 3 columns. What I will do is, I will draw a black line through this, so you can see that they essentially refer to 3 sediments which are numbered here, 6, 10, and 3. I have taken the sediment from the book of Pettyjohn, a very famous sedimentologist. So I have taken this number. So this is one sample, number 6, there's one sample, number 10, and there's one sample, number 3. And on the left-hand side in blue, say for sample number 6, you have certain numbers. These numbers are called frequency. Frequency of that number. That means out of the total weight of the sediment that what is in the sieve, 6.3 weight percent had the size range of 16 to 8. So you have taken some amount, 5 kilograms or 5 grams or 10 grams or some amount, and then you collected in different sieves. So in the size range 16 to 8, 6.3 weight fraction or weight percentage of sediments were collected between these 2 sieves, limited by 16 and 8 millimeters. So you can see 6.3 between 8 to 4 millimeter diameter. This was 11.3, 4 to 2 millimeter diameter, 20.1, and so on. And if you add these total, it will add up to 100. So for sample number 6, for example, this is what is called the frequency of the sample, or the weight percentage of the sample collected in the sieve. So this is the proportion in which the samples occur. And the red, and then next to it is a red. You can see this is called the cumulative frequency. It's called the cumulative frequency. How is it done? For those who had statistics in class 12, I think it should be easier, but those who don't have. So it is, you see it is 6.3 and this is 6.3, and this is 11.3 and this is 17.6. So what is it? 6.3 plus 11.3, that is 17.6. So you added these 2 up and made it into 17.6. And then 17.6 you added with 20.1, and this adds up to 37.7. So this is what is you are accumulating the total number of weight fractions. So this is called the cumulative frequency. So this is called the interval, the class interval, and the midpoint of it, that is say 12 millimeters here, 16 and 10 millimeters is the 8 and 16, yes, 2 millimeters is the class median. The median value of the class is 12 millimeters, but this is the class interval. For this is the class interval, this is the frequency. For class interval 8 to 4, this is the frequency, and this is the cumulative frequency. Have you understood? So if you add them up, you see when you come here, the last one, it should be 100, because that's the total percentage that you have. So we have collected one sample has, you see, this is the cumulative frequency. This adds up to 100. It should typically add up to 100. Normally the value varies from 99.9 to 100.1 because of errors, etc. So this is the value that you have. Now, if you look at the second sample, which is sample number 10, again you have the two columns, but here there are blanks. Meaning what? That no samples, if you took the whole sieve, there are no samples between 16 to 8 and 8 to 4 size range or class interval. You don't have any sample. You don't have any sample. No samples were collected in those sieves. So they're left as blank. And then between 4 to 2, it's 1.4 millimeter. Now remember one thing, just a cardinal thing, the size range of sand is 2 to 1 by 16. So this line and this line, between these two lines is what is called sand. Have you understood? This is from the wooden Bedford scale. Now I leave it to you, this is called something, this is called something, this is called something. You know, cobble, pebble, boulder, it's for you to find out. But just to give you a hint, 2 to 1 by 16, this is the sand range of sand sized particles. Below 1 by 16, remember, you had placed clay and mud and clay and all those classifications. So what is happening is, here, for example, in the coarser size range, nothing has accumulated, so it is 0. But as you go down, you can see 1.4, 1.4, 10.0 and 11.4. 11.4 is 1.4 plus 10.0 is 11.4. 11.4 plus 30.4 is 41.8. So that's how this is the cumulative percentage. And this is the third sample, set of sample, where you can see nothing has been collected in the sieves of 16 to 8, 8 to 4, 4 to 3. Nothing has been collected. And you see, what at this point you have for 2 to 1, which is the coarse sand, for example, 0.1, 0.1, this is 0.3, this becomes 0.4, 0.1 plus 0.3, 0.4. And then this is 37.8, which means 0.1 plus 0.3 plus 37.1, this is 37.5. So this is what is the cumulative frequency curve. So using this diagram, why I have tabulated it, it is because to show you this is how a grain size classification is done from essentially a sieve analysis of unconsolidated sediments. I'm talking of sediments, not sedimentary rocks, because I told you this type of analysis cannot be done in sedimentary rocks, because sedimentary rocks are lithified sediments. So you cannot separate each grain individually. You can break it, but if you break it, then the original character is gone. So that's it. Now, these 3 samples, with these 3 samples, you can plot something called a histogram. One word that is called a histogram. Or you call it a cumulative frequency diagram. Cumulative frequency diagram. What happens in this? In a histogram, say for example, there's a histogram, I will erase it, I'm just drawing it, I hope you can see it. If a horizontal axis where size ranges are given. Size ranges are given. And on this side, you have frequency. So this goes up to, 0 to 100 is the frequency. I'm talking about histograms. So what happens? So say for example, for this class range, and this is the median value, this is the frequency. So you draw a bar. But for this, you draw another bar. And for this, you draw another bar. And for that, you draw another bar, and there is nothing. So what happens? These bars, essentially, these different bars in a histogram, this tells you that this is the amount or the frequency in which this class interval occurs. Have you understood? In a cumulative frequency, what you do, you don't plot. Here what you have done is you have plotted this versus this. But in a cumulative frequency diagram, you don't do this. You plot diameter versus cumulative frequency. And this is what I have done in the diagram on the top left, frequency diagram. And this I have done for all the three samples. Histograms are good, but histograms are also cumbersome to handle. So mostly people do use histogram. It's not that people don't use histograms, but for intercomparison, etc., you would find that a cumulative frequency diagram is very convenient. This is an example of a cumulative frequency diagram. You can see the size range varies from 1 by 16 here, say for example 16, 8, 4, 2, 1, half, 1/4, 1/8, 1/16, 1 by 32. All the numbers here. 132 is not there. Why? Because you have, but you have still included 1 by 62 because there is a fraction less than 1 by 16. Less than 1 by 16. How do you do it if you don't give it a number? So this is given as 1 by 32. It is a little hypothetical, but this is the next class interval. You know, 8 to 16 to 32, each is a double parameter. 8, 16 divided by 2 is 8, 8 divided by 4, 4, 2 is divided by 1 divided by 2. So 16 divided by 1 by 30. So you create a class interval so that you can plot your points. Now you see, once I have this, remember 2 to 1 by 16, this is sand. And these are cobble, pebble, have you understood? Boulders, cobble, pebble, etc. I've given you the sizes. 1 by 256, 1 by 64, 64, 2 by 56, 4. I've given you all the sizes of the wooden number scale. But this is the sand part. Now, what I have done is, against this class interval, 16, say I take the sample 6. So in 6, between 16 to 8, so let's say there is some value as around 12. At 12, I plot 6.3. My diagrams are not exactly correct. I was doing with my hand. I plot 6.3. Then, for 8 to 4, that means 6, I plot 17.6. Have you understood? It's already more than 17.6. So like this, I go on adding the points. Have you understood? And then I join the points. Have you understood? I join the point. For 16 to 8, I have a value which is 6.3. Between 8 to 4, I have the value 17.6. From 4 to 2, I have the value 37.7. And it goes on adding. And finally, when your last value comes, it should add up to 100. And then I join all the points. So this gives you the cumulative frequency curve. Cumulative frequency curves are easy to handle. And you can superimpose several samples or a whole multitude of samples to show what it is all about. Right? So, here for example is, you know this data 6, 10 and 3, the cumulative frequency curves are seen. And this data is for 6, this is for 10 and this is for 3. They are not deadly accurate, they are approximate. I've done it with my hand, but you can do it on a graph sheet. It will be fantastic. Remember, this scale is slightly different. Remember this scale. Yeah, it's slightly different. And this is the frequency. This is the frequency. Or weight fraction, as I told you. But this is cumulative frequency. In a histogram, this vertical axis is not cumulative frequency. It is the frequency of the sample, of a particular class set side by side as bars. This is the frequency diagram. Now, in the frequency diagram, there are certain important aspects. I will tell you that. One is called the average. The average size of cell. Say in a class, you have your classmates who are 5 foot 2, 5 feet 3, 5 feet 4, 5 feet 7, 5 feet 6, 5 feet 3, 5 feet 8, 1, 6, etc., etc. And someone asks you, okay, what is the average height of your class? What you do? You find out, divide, take it all and divide by 3. This is called average, or the median value, which is at this point 50 here. 50th percentile gives you the median value of whatever it is of the different samples. So if I take a line and I draw a line 50, my diagram is not correct, you see, this is much more, this is less. You ignore all that. But this is the size of 6, mean size of 6. This is the mean size of 10. And this is the mean size of 3. So you can see on an average, 3 is finer sand and 6 is floating between 2 and 1, it's coarser. So immediately you see that 3 is finer sand and 6 is coarser sand, 10 is close to 3. And they are all in the sand range, 1 by 16 to 1 by 2. So they are not fine sand, they are coarse to intermediate size sand. Have you understood? These are not fine sand. So that's the median value, the average value. Now immediately one thing comes to your mind that okay, I get the average value, but there is a dispersion in the average value. A dispersion in the average value of your classmates in your class. There is a dispersion. So there is a mathematical symbol to calculate it, and this is given by this symbol, this calculation. So essentially in sedimentary rock, this is called sorting. S-O-R-T-I-N-G, sorting. What is sorting? It is Q3 by Q1. Now you see what is Q3. Q3 is is the 25th percentile. Do you see? Q3 is the 25th percentile. And Q1 is the 75th percentile. 75th percentile. 75th percentile is 75th percentile is Q1 and 25th percentile is Q3. That means Q3 is coarser than Q1. Now, if those of you who read newspapers or therein, you will hear a term in the first quarter, in the second quarter, in the third quarter, in the fourth. Have you understood? So that quarter, that's Q3, Q1. That is every 3 months is one quarter. So you must be reading quite a few that in this quarter there is so much depression, so much enhancement of motor cars, etc. compared to last year, compared to the average of last 10 years. This is what they're trying to do. The first quarter, the second quarter, and the third quarter. First quarter is the 25th percentile, second quarter is 75th percentile. So Q3 by Q1. Now you see here, if Q3 and Q1 are same, means what? Q3 and Q1 are same. Means what? These curves have to be straight. Yes or no? These curves, if Q3 and Q1, here you see in this curve, say for example in curve number 3, this is the value of Q1 and this is the value of Q3 for this. You see, if you now divide Q3 by Q1, you will not get a value which is 1. It would be larger than 1. So, but if you take, for example, this graph 3, here you see the value Q3 and the value of Q1 is much closer. So the value Q3 by Q1 is close to 1. What happens if Q3 by Q1 is 1? Then the graph is very straight. Have you understood? Because Q3 by Q1 is 1. So the value, the grain size of Q3 and the grain size of Q1 is 1, but one is the 25th percentile, one is the 75th percentile. That means that sediment is very well sorted sediment. They are very well sorted sediments because they have a very, very uniform size. So if your sorting value, which is the dispersion, is Q3 is Q1 is close to 1, that means the graph has to be steep. Have you understood? Graph has to be steep. Only then you will have a well sorted sediment. But if you have a poorly sorted sediment, then you can understand your graph will be tilted. So the larger the value, the poorer is the sorting. The larger is the difference, the poorer is the sorting. Have you understood? So poorly sorted sediments have a shallow slope, but well sorted sediment have a steep, near vertical slope if it is an extremely well sorted sediment. Normally, what happens in the beach, if you take beach sands, they have very well sorted. Why? Because, as I have told you, that the sorting will improve. The sorting will improve in two places. One is during transportation and during deposition. If you give, for example, in the depositional zone, if you have a thick water column and a sediment deposited according to size, the settling velocity, then you will have very well sorted sediments in the depositional basin. But you can say you have a poorly sorted sediment that comes to the deposition basin. But the deposition basin has a huge water length. So what happens? Sediments will be deposited and you will have at different levels, you will have wonderfully sorted sediments. We will come to this topic later on. Or else, in the sedimentary basin, you could bring in very well sorted sediments, not poorly sorted sediments. Very well sorted sediment. Then, of course, the settling velocity does not do much because all the sizes are the same. R is the same, and if they belong to the same mineral, then the density is the same, so everything is the same. It just simply sorts it out. Right? And so that is what is happening. So when you have a well sorted sediment, there are only several possibilities. If you have a well sorted sediment, either the sorting was done at the deposition site or the sorting was done at the transportation zone. Have you understood? So you could have brought in poorly sorted sediment. Have you understood? Poorly sorted sediment and then deposited in the long water column. So you will have well sorted sediments at different levels. Or you could have brought in uniform sized sediments and deposited in a basin. There could be no further sorting because the density and the radius are all the same. So this is what is important. The beach sands, what happens, although the source and the deposition site may not be very far, but as I have told you, in the sediment, in the beach sands, what happens, the waves bring it in and bring it out, bring it in and bring it out. So although the distance traveled, total distance, single cycle distance, it's not much, but if you take multiple cycle distances, then you get very well sorted sediments, as you can understand. If you transport sediments over long distances, you will have very fine sediment. If you go to the Bay of Bengal, for example, there the sediments are very fine, clay sometimes, and very fine sand to clay, and they're very well sorted. But if you are in the Himalayas, for example, wherever you go, you will have very poorly sorted sediments, because it's all dumped. Right. So this is what is called sorting. So you have mean size and you have sorting. And then, this is the next important point. This is called the symmetry of the element. What is symmetry? So I will show it to you in a histogram. That will be better. Say, for example, I have, this is a histogram. where they say size increases this way and this is frequency. What is happening? Although my mean value is somewhere here and mean value is somewhere here, but you see the coarser parts, same as this, the coarser part has higher percentage, while the finer parts have smaller percentage. Do you understand? And you could have the other way around also, where the coarser particle have smaller frequency and the finer particle have very high frequency. This also can be done. We will talk a little bit about this in maybe not in this lecture, but maybe in the next lecture. So, and how is this calculated? This is called skewness. The term that is used here is called skewness. Skewness, average we have discussed, sorting we have discussed, now we are doing skewness. So sediments are skewed to the coarser sizes, or sediments are skewed to the finer sizes. Or you have a perfect log normal distribution, a perfect Gaussian distribution, where the mean value is the highest and falls off on either side. Yeah? So this is what is called a symmetry. And the way to calculate it, a simple method that was designed long back, but now it has been improved and re-improved. It's Q1 into Q3 by MD squared. Looking at it simply, I can just rewrite this equation and then I think you will understand it better. I can write Q1 by MD into Q3 by MD. Now I think you can understand it better. See here, Q1 by MD into Q3 by MD. So this is the median value, and for 6, for example, this is Q1. So this is the Q1 value. For 6, this is the median value, MD. So Q1 by MD into Q3 by MD. Have you understood? Now, let's assume Q1, it is a very well sorted sediment. Very well sorted sediment. If it's, let's say it's a very well sorted sediment. So Q1 will be almost equal to Q3, would be equal to MD. Therefore, Q1 into Q3 by MD square, you will have a value 1 for a perfectly sorted sediment. Because Q1 will be equal to Q3, the grain size at Q1, the grain size at Q3, and divided by MD, you will have a value of 1. As you disperse, you can have decimals and values greater than 1. So 1 is for negatively skewed and 1 is for positively skewed elements. In one is finer size materials that is skewed up, and the other, the coarser size material, are skewed up. So it gives you, all these parameters gives you a variation in the density, it's a size distribution of the sediment. And once you have the size distribution of the sediment, you can try and find out, okay, what was the dynamics of movement that created these sediments, right? Now the last parameter that is there is called pickedness. Pickedness, and this has a term called kurtosis. Kurtosis. Kurtosis is the technical word for it. It's called the pickedness. Pickedness means how sharp is the peak of the histogram. How sharp is the peak of the histogram. That is what is called kurtosis. It's not the value that is important. It is the sharpness that is important. How sharp it is. So one is the median value and one is kurtosis. They are not one and the same. Median value is the median size. Kurtosis is the amount of peakedness. How much high frequency is the median value. That is what it looks after peaking. And you can see how this is calculated. Q3 minus Q1, Q3 minus Q1, so you get the value, Q3 minus Q1 divided by the sizes at P90 minus P10. What is P90? P90 is here, percentile 90, and this is percentile 10. this is the 10th percentile, and this is 90th percentile, and you can see you are taking, for example, for the sample 10, this is the value that you're getting, and for 10, this is the value that you're getting. So that is what it is, P90 minus P10, and that is the value that you're getting for co-process. So this is the expression that is used to find out. You can see these are the two extremes. So this is the value that you find out to find out the pickedness of the sediment. So from the cumulative frequency diagram, we can arrive at certain important statistical parameters that we would require to understand either the dynamics of the deposition or the dynamics of the transportation, or for example the total dynamics of the system. As to what we see, we will try to get a value to it. Have you understood? That is the most important thing of this statistical analysis of sediments. But one thing I must caution you, I have only told you given simple formula. These formulae have been polished and refined and re-refined by several authors, and in some books you might get it different. This is the one that was used very early by Petitjohn, for example, in his book, and this I have given him. So once again, just to repeat, there are certain important things that you should learn. You should know class, and then class interval is one, and the class median. Class interval and class median. 16 to 8 is the class interval, 12 is the class median. And then you can have the frequency and also the cumulative frequency. Cumulative frequency is the one that you go on adding the frequencies, and this will add up to 100. This is 100 below, and this will add up to 100 when you have added the last class interval. That's called the cumulative frequency. And then when you plot your class interval with the cumulative frequency, you will generate a curve like this. You will generate different shapes of curves from which you can find out several statistical parameters like median, like sorting, like skewness, like kurtosis. All these terms you can use to do now the next step, the dynamics of the process that eventually led to its transportation and deposition. We will do that in the next class. I don't think we will have the time now, but quickly we can, in 5 minutes, just for us to get acquainted to cumulative frequency curves. Just a moment. Say, for example, I draw a cumulative frequency curve like this. You know the frequency varies from 0 to 100, and this is grain size increasing. And I have a cumulative frequency curve. Like that. What does this mean? What does this mean? This cumulative frequency curve, what does it mean? There are certain fractions. If you divide this curve, there are certain parts here. What is this part? Remember how cumulative curves are added? So you had a particular value and then you are not adding very high values, you are adding near zero values. Again, after this size, these values drop. You can see the steep increase of these values. What does it mean? It means that these sizes are close to zero. That means the weight fraction of these sizes is very small. That is why you get a flat slope. That, in other words, this size is very prominent and so is this size very prominent. So this has two dominant grain sizes. Have you understood? Two dominant grain sizes. Here and here. The intermediate sizes are almost non-existent, or maybe they are very, very small. So I take a sediment, obviously then the sediment, the detritus or the clast is two-sized. Now the other question is, how does it come? How does it become? That is a different. But what is important to realize is that this means a bimodal grain population. Bimodal grain population. Have you understood? So, but if I say this and instead if I draw a size like this, means what? Say for example, this will be the median value, MD, this is Q3, remember, and this is Q1. So now, you can see here already, in the blue in this graph, which has a steep slope, the value of Q3, Q1 and Q3 is the same. So what is happening? The sorting parameter, which is root over Q3 by Q1, that is equal to 1. So it's a very well sorted sediment, and this is the value of MD, which is also close to Q3 and Q1. Therefore, Q3 into Q1 by MD square, which is an expression of the skewness of the sample, it's also not there. Because Q1 into Q3 by MD square, all are equal the same. So what will happen? You will have a value close to 1. So those are very symmetric distribution. Very, very symmetric distribution. That means there is a very small population here. So in a distribution, this would be something like that. You will have a small population here which is small, a small population which is coarse, and you have very unimodal size. As opposed to this blue one. You can see this point here, I will draw it in blue or black. Say for example, this is the, you see this is the problem. This is MD for the blue graph. You say it is giving you an average size, but there are no grains of that size. There are no clasts, there are no detritus of that size. It is just giving you a mean. Just like, say I am 5 feet 5 and my student is 5 feet 7. So the average height is 5 feet 6. Although there is no one in the room with a height 5 feet 6. It's just like that. So I am 5 feet 5, my student is 5 feet 7, average height 5 feet 6. There is no one in the room with 5 feet 6. So that is what it is. You have a grain size here, the median value comes here, and you don't have a grain of that size. And then you take root over Q3 by Q1. So you see, this is the value of Q3, and this is the value of Q1, and you see this is a very poorly sorted segment. Just the opposite of the red sample. It's an extremely poorly sorted segment. Although the median value of the two sediments are the same. But one, the blue-red one, is very well sorted, and the blue one is very poorly sorted, and with a bimodal grain size distribution. So, as you know, statistics, one says that if you put your head in an oven and your leg in a refrigerator, on an average, you are comfortable. So that's statistics. So here also, it's the same. Both give you the same MD value, but the two sediments have completely different structure. And then you take out the skewness part, root over Q1 into Q3 by MD squared. Q1 into Q3 by MD squared. This is what is skewness all about. And now you see, this is your Q3 for the blue one, this is your Q1, and this is your MD squared. You will have a very different, you have a value very different from one. So this sediment in blue and this sediment in red, they have completely different dynamics of transport and deposition. They have completely different dynamics of transport and deposition. So just the median value does not mean much. Right? Okay. This lecture, we will continue with the sorting, etc. in the next lecture. Thank you.